Can you hear me? All right. What you see here is what on the left, we have what we started with last time. All right. So what we did was to remember, just to remind you, to remember how the field changes when the charge is over an infinite large planar surface. And how does it change? So I'm asking you. Constant. What if your charge is along an infinitely long line? How does the field due to this charge change? 1 over the distance, right? And what if your charge is at one point in space and your field is changing like how? Away from the charge. Remember?
1 over square.
Yes, 1 over distance squared. Okay. Also, what we saw, it was something interesting. We got the charge to distribute over a volume. Remember that? And then what you solved as problem is the charge to distribute within a dielectric volume, but uniformly. And then what do you find if you go away from it? That the field changes outside. I mean, if you go away from it, how does the field change? If you are outside of this volume, as if it's a spherical volume. It changes as 1 over distance squared. What does that tell you? That if you have any type of an antenna, anything, you can have a dipole, you can have a loop antenna, you can have a horn antenna. I mean, if you, those of you who will go into that direction, you're going to see all kinds of antennas. What happens if you are away from the antenna? What do you normally see? You see a field that changes as 1 over the distance squared. Nothing changes that. The value of the field may change. It might be not uniform in the whole space. It might have more what we call a major lobe, means stronger in some areas and weaker in some other areas. But if you take one line that connects you to the charge, to the antenna, and then you start moving away from it, the field changes as 1 over r squared. All right, that's always the case. All right, going into parallel plate conductors. In this case, we said if the charge is uniformly distributed over the area of one large parallel plate planar conductor, it's a constant. Now, what if this conductor we said there, it has negative charge distributed evenly, creates a field like this, which is the green one, going towards the negative charge. You remember the field lines always go toward negative charges and away from positive charges. So the field lines is not like the electric field is not just having a magnitude, but has a direction. And in the direction is as important as the magnitude. So for charges that are distributed uniformly on a planar surface, the field is constant, but always perpendicular to that surface. If the charges that are distributed on the surface of that surface on conductor are negative, the field will be perpendicular. It will be constant, but it's going to point towards the negative charge. And if we take another conductor on top of this, that has the same more or less charge density and distributes evenly, then the field that is created from that positive charge is going to be constant, is going to be perpendicular to the parallel plate on which the charge rests, and is going to point opposite, away from the positive charge. That's the red one. So the two together, if you sum them up, you're going to find the total field that is created between these two conductors. And the total field has this value here. So practically to remember it is this one, is the charge distribution divided by epsilon. And epsilon is the product of the relative dielectric constant epsilon sub r times epsilon naught, all right? But it is Q sub s divided by epsilon. That's the field between two parallel plates that have charges. And then we said, how can you really put these charges on these two parallel plates is by connecting the plates to a battery, all right, that has a positive pole and a negative. The positive side of the battery supplies all of this positive charge. The negative supplies the negative charge. The two charges facing each other are attracted. So they're going to be on the side of the conductor that brings them the closest against each other. So they're going to be on the lower surface of the upper conductor, the upper surface of the lower conductor. And they're going to create that total field, all right? And then from the value of the field, which is Q sub s, this charge distribution, divided by epsilon. Here, the conductors, like in a capacitor, because this is a capacitor, the conductors have a finite size, but we still assume that it's a uniform distribution. It's a good approximation. The area is A times B. And from the charge distribution, which is Q sub s times A times B, you find the total charge. So there is a positive charge Q sub s A times B here on the upper conductor, and the same negative charge on the lower conductor. And from the value of the electric field, we find the voltage, which is the integral here, this integral. All right, this is the integral that comes out of the relationship between the electric field and the potential. I've seen this before. And then from the voltage, which is here, and from the total charge, which is here, we now define what? Define the capacitance of this parallel plate capacitor that is given. It's a function of only the geometry and the material properties, nothing else. It's not a function of the voltage, it's not a function of how many charges you have, up, down, whatever. All right, it's a function only of epsilon, which characterizes the dielectric material, area, and the distance between the two conductors. A question for you. Let's assume, you remember what we said about materials, that every material has which two parameters that characterize it? Epsilon and mu, remember that? Epsilon only, and mu naught makes dielectric materials. Epsilon naught and mu makes magnetic materials, all right? So every material in the world has two parameters, epsilon and mu. All right, and we said that this can be a scalar, can be a tensor, can change with time or whatever, but the materials here will be homogeneous, isotropic, and linear, all the good properties, which means epsilon is going to be a scalar, it's going to be the same everywhere in the material, and it's going to have a constant times epsilon naught. All right, that's for free space, epsilon naught. And we know how much the value is, 8.854, 10 to minus 12 farads per meter. All right, mu. This is called the electric permittivity. And this is called the magnetic permeability, the names. You have seen those before. The same way with epsilon also is mu. Mu can be the product of a constant mu sub r times mu sub naught, where mu sub naught is the magnetic permeability of free space. And I don't quite remember the value, but it is in the book front page, or you can find it wherever. When we start with magnetics, I will start memorizing that, then I forget it. All right. When materials have this mu and mu sub r is above 1, we call them magnetic materials. When materials have this epsilon r above 1, we call them dielectric materials. Of course, there are materials that can have both. All right, and they can have some kind of dielectric properties and magnetic properties. All right, but here we're going to see them separately in this class. Okay, question for you. One very important question. Think about this and then you will respond. If I were to take this on the left here, on the left, and replace the material, the yellow, with a material that is magnetic. It has a mu. And this material now, the magnetic material, is going to have epsilon equals epsilon r, and mu equals mu sub r times mu sub naught. And mu sub r can be a very large number. It can be 10 to the 5th for good magnetic materials. What is going to happen to the capacitance? What do you think? Think. How, look at what entity, electric entity, did we use to find the capacitance? Think about it. We started with discussing what? The electric field. You remember that? The electric field comes from what? How did we define the electric field? We defined it from the electric force. All right? Do you remember the electric forces between the two charges? Coulomb's law? Do you have any mu in there? No. Electric forces do not see any mu. They see only what? Epsilon. All right? There is only epsilon in an electric force. Do you remember any mu in those electric forces? Do you remember any mu in the electric field? All right, so what happens? The electric field does not see that mu, does not impact it. The only thing that impacts the electric field is epsilon. So what is going to be the capacitance of this capacitor with the magnetic material? Same this one. Why do we not use magnetic materials? Because they're very lossy. Why would I put a lossy material in a capacitor? It's not like that I don't have a reason to do it and make it a loss capacitor, so it has resistance, all right? So, and why they are lossy, we're gonna see later. But why is that? Because they have iron in there or something like that. Usually there are. In the magnetic materials work because there are small dipoles that go like this. Like an electron will go around, will not move like a free electron, but it's gonna create a circle. Like it's gonna go around a circle, it's gonna create small currents, all right? And because the electrons do that constantly, and because mu sub r is very high, so they have a lot of loss, all right? I mean, from scattering and other things. So the loss inside the magnetic materials is very high. That's why we don't put them in. They're very expensive too, and very difficult to make them. So we go for dielectrics. Okay, so that's one question for you. So you remember, capacitance has nothing to do with mu. Now, these capacitances are very popular in circuit design. We call them an MOS capacitor. Usually the way we make MOS capacitors, let me remove this for a moment. Okay. Okay. So an MOS capacitor, you have a silicon. It's like the name is metal oxide silicon. So we have silicon here, a very nice and big wafer. You know how big the wafers are silicon nowadays that they go and print them? 16 inches. That's how they go into the foundries, and they make all kinds of circuits. So this is pretty thick, obviously, but it's silicon. And then what do? Are they going? Silicon is like low resistivity. When we say low resistivity silicon, means you have kind of losses in there from impurities and other things. There is high resistivity silicon also for high fingers, but low resistivity silicon is what people are using for all the CMOS-based applications. So if you have silicon, you're not going to use silicon to create a capacitor. First of all, the capacitors are tiny. They need very small thickness, and they need no losses. So what they do, they put a silicon oxide here. And the silicon oxide can be like from a micron to less, or a fraction of a micron. And then what do? They put a metal here. And then of course they have another metal here because they want the field to be combined. And that's an Mos capacitor. Very popular. All of the things that we're using about the Mos capacitors is like exactly what we know here. Okay, so here we have the following problem. And let's try to understand how to solve it. Now I have a 3 metal plate structure. It's like I had here another, and I'll tell you why this is important, because you may have that may be one type of a line going like this. You've seen these lines. And it may be part of a capacitor here. And then here you may have another layer, and then you may have a line that goes parallel to this. So the lines have a cross section. So there is an overlap. And this, for example, overlap between multiple metals, simplified, can be represented like this. Okay, so you may have multiple metals, since some of these CMOS-based architectures may have up to 17 layers. 17 layers for vertical integration of the interconnects and the CMOS. Okay, so you will have areas where you have multiple conductors. In this particular case, a very simplified problem, but it shows you how to understand what is the capacitance, because if you have multiple conductors at different potentials, there is going to be capacitance between them. What creates capacitance? The voltage applied across the conductors. If there is no voltage applied across the conductors, what does it mean? There are no charges, there is no electric field, there is no capacitance, all right? The moment, so therefore in equilibrium, if we have all of these conductors, but none of those is excited by anything. So like if I turn off my computer, all of the microprocessors will be turned off with the exceptions of some memories. Everything that does processing is not going to work. Therefore, I don't have any capacitances. I don't have anything in there. The moment, however, I turn it on, then a lot of the metals go to different potential. And if they have different potential, then there is capacitance in between them. And if there is capacitance in between them, then they have crosstalk, as we say. What is the crosstalk? Exactly the way I will explain it here. Okay, so let's see what happens when the metals talk to each other, as they say. Here I show that two of these metals, they are at the same potential, up and below. And I saw that I apply the same potential for two batteries, all right, which are identical. And then the middle one goes ground. So let's see what happens. First of all, we want to find out what happens, how many charges are now located on the various conductors. All right. So let's see. You have the positive pole of this battery connected to conductor 1. And therefore, you have a plethora of positive charges. And because the positive charges see each other, they will balance themselves out. naturally, without any other impact, they would go and distribute evenly. Now, they could go to the upper part of the plate or to the lower part of the plate. Where they go depends on what happens on the other conductors next to them, all right? So if this conductor is at a different potential, ground here, and the ground is like a sea of negative electrons. It's like a source, an infinite source of electrons or an infinite sink of electrons. You can put as many electrons in there as you can, nothing is going to happen. And you can draw as many electrons as you can, and nothing is going to happen to the ground, all right? So here is 0. What happens therefore? Because of the positive charges, negative charges come from here, and they take a position to see these positive charges. If this conductor underneath it was also at 0 potential, only the negative charges here would be across the positive charges. Nothing else. Here will be like no activity. But now, because of the charges up here, which we don't know what they are yet, Q1, you have a minus Q1 of charges distributed evenly in the bottom, on the top surface of the middle ground. We go here. We force this potential to be at VP. So another set of charges comes here. Don't know them yet. And because of this, then there is another set of electrons, same in size with this, and they are facing them. All right? So what happens here? You have charge Q1, you have a charge Q3, and then you have charge minus Q1, minus Q3 in the middle one. And those all are excited because of the initial charges. So practically, these different potentials have developed these different charges. And now these conductors see each other. That is called crosstalk. They're tied to each other through the charges. And what is going to happen? You're going to have one capacitance here and one capacitance there. And if this conductor was extended even further from this, but this was terminated, it would have a third capacitance between the upper one and the lower one. So you have all of these capacitances, which we call them parasitic capacitances. All right, and crosstalk between the conductors. Because ideally, when you design a circuit, you want your every conductor, which is a line, everything that is metal, you want it to be excited independently and operate independently. However, nothing happens independently in circuits that are very crowded. They're very dense. This one, you know how many transistors, CMOS, there are here? Say a number. How many? 500 billion. 500. It's a few. It's very few. It's not. It's a large few. Whatever. There are few. 500 billion. 100 billion neurons in our brain. 500 billion here. All right, and it's not as smart as our brain, anyways. But 500 billion transistors in a small area, you know, because the biggest part of this is the battery. Have you opened one? The old ones that you have, opened them up to see how they look. Okay, open them up to see the battery, to see the RF front end, to see all of the other, the processor. They're all small pieces. The camera and the battery, and you leave a tiny piece for the receiver that's transmitted. So the 500 billion transistors are in a very small area. Therefore, you can imagine that all of these lines are probably a micron thick over a few nanometers away, all right, crossing, you know how many trillion of lines you will have for 500 billion transistors? 100 times more lines. All of these are close to each other. And if somebody like me were to go and design it, nothing would work. even if I know some things, all right? But there are, of course, design rules. But in any case, all of these are important to know. So how are we going to find out the Qs? We found more or less how they're going to look, but now we have to calculate them. Okay. What do we know about the voltage and the capacitance? We know that the voltage relates to the capacitance, and the capacitance, well, relates, of course, but the capacitance here is independent. The formula, it only depends on the geometry and epsilon. So we can find the capacitance for here from the geometry. This is area, A, and the distance, and epsilon. So this is our capacitance, all right? A times epsilon. It's A times epsilon divided by H. But what other thing we know about? So we can calculate the capacitance here, 0.5 picofarads from that simple formula. Then what else do we know? That the capacitance is the ratio of Q1, this is Q1 up here. In this place, we see Q1 here, Q minus Q1 there, and nothing else. The electric field between these two plates right here does not see anything of this. It sees only plus Q1 here, minus Q1 there, and the dielectric here, and the voltage, VT. So we have that C is equal to total charge Q1 divided by VD. Since we know V sub T was given to us, we know the capacitance, then we can find the Q1. And we found that Q1 is 1.7 picocoulombs. All right. Now we go to conductor. The charge, this is the charge on conductor 1. Now we go to the space between conductor 2 and 3 down here. Same thing. I find the capacitance here, which depends on VD, on H, and epsilon R. These two capacitances will be different because here we have epsilon R, and therefore the capacitance is going to be what? Higher or lower? No. Higher. Okay, higher, lower here. So the capacitance here, we can calculate it. And from the capacitance and VD, we can find Q3. So what do we find? C2. Let me see. Yeah, C2 is lower. Of course, higher is C1. C2 is 0.141 picofarads. From there, from this relationship, we'll find Q3. So now we can go and say the following. Since we know Q1 and Q3, then we can say Q1 is this many picocoulombs. Q3 positive is this many picocoulombs. And then in between, the conductor in between has the sum of these two negative ones. All right, so we found the three charges to be Q1, 1.7 picocoulombs, Q2 to be the sum of the two negatives, and Q3 to be another positive. All right, so at this moment, we have found the charges. Okay, any questions so far before we proceed? Q3 or C3? There is no C3 yet. Q3. There. Okay. What is question B? Ask. B says, find the total capacitances seen between points A and B. So we want the total capacitance between A and B between B and C and between A and C. So now we are in circuit form. I'm not going to stay. They ask me a circuit question. They're asking me to find the capacitances. And I'm not going to stay with this three-dimensional structure, right? That's why we go to capacitance. We don't have to go to a three-dimensional structure, which is complicated. So I'm going to go and create this simple circuit. Do you know how to find the capacitance in this, the capacitances in this simple circuit? Now, what is the capacitance in between A and B? The capacitance on the first one, C1. What is the capacitance between B and C? The capacitance in the second piece, all right? And then what is the capacitance between A and C? That was the one that drove a lot of people crazy, the question. Because, why is that? What is the capacitance between A and C? What would you do to find a total impedance? You remember, this is like a circuit question.
Add them in series. Add them in series.
Can you? No, because there is a ground in there. What would we do to solve this problem? Do you remember when you go from a star configuration to a delta? Do you remember when you try to find the Thevenin's or, the Thevenin's equivalent impedance or Norton's? That's what you have to do. You cannot say series because, there is this ground and the ground messes you up. Why it messes you up? Because you have extra charges that go. If the ground were not there, yes, it's a series combination. But the ground there is a problem. Every time you have a ground and you don't take it into consideration in circuit design, in circuits, simple circuits, then you have a problem. Grounds are important. All right. Okay. Next one. What was the second? C. Consider now that there is no connection between points B and D. All right. And find the capacitances. Now that is the series at points A and C. Let's see that one. Okay, there we go. What is different right now? Can you tell me a little bit why this structure, and of course you have a series capacitor, why this structure is different from the one above? Now I just have removed the ground connection between B and D. Look what I said here. For this particular, well, let me see, make sure that I don't, make sure, 1 second. And the yes. Okay. This case. First of all, talk about the capacitance. What happens here that is different from the one above? Can somebody explain to me why this one is different from the one above? I have a BD. All of the positive charges will come here. All right, as above. Plus Q1. All right. Let me write so. So let's see here. As I was before, let's assume that I have all of the positive charges here. Q1. Okay. What happens to the ground underneath it? because of the positive charges, all of these free electrons that were swimming here, happy and everything, without committing to anything, they will have to come and face them. They will be attracted to them, and they will go to the place that brings them the closest, which is down here. Okay, so far so good. We see electrons coming back. However, because this metal is not connected to anything, like nothing, what is happening underneath it? What is happening? What is going to happen if the electrons move there? What is going to happen? The holes are going to be, yes. So here, the holes will be here. But then what? The other voltage here forces more holes here. More holes. Which in fact is going to push all of these holes up here away. We try to go to the other side, and they're going to cancel all of the electrons. So in this particular case, if they cancel all of the electrons, okay, because they're going to be pushed away by the others, so they will go, all of the holes, they will move away, and they will go up here. Change the color also. And they will cancel all of the electrons. All right. And then without any charges there cannot be charges here. And without these charges here, there cannot be charges there. So what happens in this case? There are no charges. If there are no charges, does that mean that there is no capacitance? That's a big question. Since there are no charges anywhere, does that mean that there is no capacitance? Because it asks me to find the capacitance between A, B, and C. Could you speak a little louder? Exactly. The capacitance is independent. The capacitance has nothing to do with the excitation. The capacitance is telling you that this structure has the capacity to store electric field if it is excited. It's like, for example, you go to the elevator and say capacity 4 people. And maybe there's nobody in there. The fact that it has a capacity for 4 people is not depending on how many people go there. All right, it's a capacity. When you say I have a capacity in this room of 150 people, the room a lot of times is empty. But the capacity is there. All right, the capacitor is the same. So you can have capacitance but not charge. All right, the capacitance means that they are so close to each other that if there were charge, then I would see a field that is important. So 0 charge for this, but the capacitance exists. And how do I find the capacitance? From here? It's a series capacitance. I'm not going to go and solve the problem again, all right? I have point A connected to point B here. That's point B. And then through C2 to point C. So the capacitance between A and B is C1, B and C is C2, and how much is between A and C is the series combination of the two. But what? There is no current. There is no voltage that is created at B. Why is that? Because even if you see here, the potential at A and C are identical. Therefore, there is no voltage drop between these two to create any current activity. Okay? So we have capacitance, but we don't have current because we have the 2 points at the same potential. So the voltage drop between A and C is 0. But that does not mean that I don't have a capacitance, all right? I have to tell you the difference between these concepts, because I had a lot of students in the class that said no capacitance. Capacitance because there was, of course, there was no voltage drop. But the capacitance has nothing to do with the voltage drop. It's a characteristic of the geometry only and the material properties. Any questions about this? Okay. That is explaining it here. That we're going to do on Friday. We're going to solve a number of problems on Friday. And this is another very popular conductor. I will just introduce it. But before we go there, I also want you to do a small exercise. So maybe I'll stop that for a moment. And what I'm going to do, I'm going to go here. Go to that, here. It's very simple. Here. Okay. Charges. Okay. Let me see what we have here. This one. Okay, I want you to do this exercise 7, and I will assign it. Assign it as homework. And the exercise, I don't want to show that because you're going to see people. Do you have access to exercise? Do it now. Now. I see some people looking at me. You're doing it right now. It's a very simple one on the basis of what we discussed. So here today, not in the previous class.